I'm Charlie and this is my project, the redesign of the prosthetic socket. There were 26,000 lower limb amputations related to diabetes in England from 2014 to 2017. Unhealed foot ulcers and infections are the leading cause of amputations in diabetic patients, as nerve damage means patients are unaware of pain from rubbing, and ulcers frequently turn gangrenous due to the patient not seeking medical attention. Sockets are a crucial part of any prosthetic system, as the connection between the user's body and their prosthetic limb. The function of a socket is to transfer the force from the user's body weight safely to the ground, and maintain a secure fit to keep the prosthetic limb in place. The socket must be perfectly fitted to the shape of an amputee's residual limb, and is a tight-fitting, rigid device that covers a significant area of the wearer's remaining limb. Currently, sockets are made from carbon fibre, which is impermeable. This causes a buildup of sweat and trapped heat, which weakens the skin and makes it more susceptible to blisters. Carbon fibre is also incredibly stiff, which causes rubbing and blisters when improper fit or excess pressure is placed on vulnerable areas. Blisters frequently cause problems for amputees, such as discomfort, which means the prosthetic cannot be worn until the blister heals, or even further amputation if the blister progresses into an ulcer. This is especially prevalent in the diabetic population, where nearly half of all diabetic amputees go on to have further amputations. Carbon fibre sockets are fabricated by hand by prosthetists, which results in inconsistent quality and mechanical strength. The fabrication process is also lengthy and wasteful. A mould is made of the limb using plaster. A clear plastic check socket is then made to visually assess the fit and pressure points, and any modifications are made in the final carbon fibre lamination. If any extra features are required, like adjustable panels, this requires lamination dummies and spacers for wire cavities, which then have to be thrown away, and panels have to be cut out after the lamination is complete. The aim of this project is to produce a new socket that reduces the incidence of blisters. The approach is twofold: by increasing ventilation to reduce the buildup of perspiration, and by introducing flexibility into the inner surface to reduce pressure and rubbing. Using polyjet printing allows for multiple materials to be fabricated simultaneously, and samples produced for this project demonstrated a strong, tough surface can be backed with a softer, more flexible layer with no splitting at the seam between the two. 3D printing can be used to create a functional, innovative design made possible only by additive manufacturing. 3D scans of patients' limbs can be used to create a socket that fits perfectly, minimizing the number of steps needed in the manufacturing process by eliminating plaster casts and check sockets, and introducing precision into the fitting procedure. The final concept is made out of ABS with a compliant Agilus 30 inner surface. It has 360 degrees of ventilation to disperse heat and keep the residual limb cool and dry. The perforations are arranged in a parametric pattern that responds to the contours of the socket, reflecting the innovative nature of the new design and maximizing compressive strength. The walls of the perforations are angled and filleted to encourage sweat to run out of the socket, and the integrated flexible inner surface cushions areas under pressure and protects the skin from rubbing. There is a built-in Bower dial system to adjust volume, which gives the user full control of the fit of their socket, allowing them to expand the socket if it feels tight or increase compression if the socket feels loose. Designing the adjustable panel system into the socket and requiring no extra steps to fabricate it drastically cuts down the time to manufacture, and the user can receive their custom-fitted, ventilated socket in a matter of days rather than weeks. The socket can also be tested using finite element analysis to ensure its mechanical properties to make it safe to use without requiring destructive testing, and adjustments to the CAD file can be made to increase strength before printing. The thickness of the flexible inner layer can also be adjusted to accommodate sensitive spots for each specific patient and deliver a truly customized quality product. Thank you for listening.